Welcome to Week 2, Module 6 of the Database Management System course in the IIT Madras online BSc program. In the last week, we introduced the course. We discussed what database management systems are, why they are widely used, and why databases are often preferred over simple file-based applications. A file-based system can store data, but databases provide much better organization, consistency, searching ability, and management of large amounts of information. We also discussed the basic ideas of databases in the previous modules. Now we will move towards more specific concepts related to the relational database system. In this module, we will understand attributes, their roles, and the mathematical structure behind the relational model. We will learn about concepts like schema, instance, and keys. We will also get introduced to the basics of relational query languages. A relation in a database is basically a table. A table has columns and rows. Each column has a name. These column names are called attributes. The order of columns does not matter. What matters is the name and meaning of each attribute. Each row represents one complete record. A row is also called a tuple. A tuple contains values for all the attributes. For example, if we have a student table, each row represents one student. Now let us understand what an attribute is. Suppose we want to store information about students. A student is a person, and a person can have millions of possible properties. For example, name, parent's name, address, hobbies, age, and many others. But when designing a database, we only select attributes that are useful for our application. This selection depends on the purpose of the database. For a student database, we may choose attributes like roll number, first name, last name, date of birth, passport number, Aadhaar number, department. Each attribute has a type. This type is called the domain of the attribute. For example, a roll number may contain both numbers and letters, so its type is an alphanumeric string. A first name is a string containing letters. A date of birth is a date type. Even though a date has multiple parts like day, month, and year, it is still treated as one atomic value. Atomic means it cannot be divided further for the database purpose. A passport number is also a string, but it may be nullable. Nullable means the value can be empty. For example, if a student does not have a passport, we store null. Null means there is no value available. It does not mean zero. It means unknown or not applicable. However, some attributes cannot be null. A roll number cannot be null because every student must have one. A first name usually cannot be null because the student must have a name. The Aadhaar number is a 12-digit number. The department name is a string. So every attribute has a name, a type, a set of possible values. That set of possible values is called its domain. For example, if date of birth has a date domain, we cannot store a normal sentence like 27th March 1997. The value must follow the date format. Similarly, if a department attribute expects a department name, we cannot store an unrelated value. Every value must match the domain of that attribute. Now let us talk about schema and instance. A schema describes the structure of the table. It tells us what attributes exist, what their types are. It does not contain actual data. An instance is the actual data stored in the table at a particular time. So, schema is the design. Instance is the current content. Mathematically, if a relation is n attributes, we write it as R with attributes A1, A2 up to n. This is called the relational schema. Each attribute has a domain. For example, A1 has domain D1, A2 has domain D2, and so on. The relation is a subset of the combination of all these domains, meaning every row must contain one value from D1, one value from D2, and so on until Dn. A relational instance is the actual set of rows. For example, an instructor table may have instructor ID, name, department, salary. The schema defines these columns. The instance contains the actual instructors. One important property, the order of rows does not matter. A relation is like a mathematical set. Sets do not have ordering. So if we rearrange rows, the relation is still the same. But another property of sets is that elements must be unique. Therefore, two identical rows cannot exist. Every tuple must be different from every other tuple. Next, we discuss keys. A key helps us identify a row uniquely. A table may have many attributes, but not every attribute uniquely identifies a row. For example, many people can have the same name. Many people can belong to the same department. Many people can have the same salary. But an employee ID should be unique. A superkey is a set of attributes that can uniquely identify every row. For example, employee ID is a superkey. Employee ID plus name is also a superkey. Because if employee ID alone identifies someone, adding name does not hurt. But it is not minimal. A candidate key is a minimal superkey. Minimal means no smaller subset can still uniquely identify rows. For example, employee ID is a candidate key. Employee ID plus name is only a superkey. Because employee ID alone is enough. A table can have multiple candidate keys. From those, we choose one as the primary key. The primary key is the main identifier used by the database. Other candidate keys become alternate keys. Sometimes data itself is not naturally unique. For example, online shopping orders. Two orders can have the same item, the same quantity, the same price, the same customer, the same date. But they are still different orders. So the system creates a new identifier. This is called a surrogate key. An order number is a surrogate key. It is artificially generated to uniquely identify an object. Now let us look at an example of keys. Suppose we have a student relation. The attributes are roll number, first name, last name, date of birth, passport number, Aadhaar number, department. Roll number is a superkey. Roll number and date of birth together is also a superkey. But date of birth alone is not a superkey, because many students can have the same birthday. Passport number may look unique, but it cannot be a candidate key here. Why? Because passport number is nullable. Some students may not have a passport. If a value can be missing, we cannot depend on it to identify every student. Possible candidate keys are roll number, first name and last name together, Aadhaar number, but choosing a primary key requires more thought. First name and last name is not a good choice. Many people can share the same name. For example, many people may have the same first name and last name, so it may create confusion. Aadhaar number can uniquely identify a person, but in an academic system, roll number is usually preferred. This is because roll number often contains useful information. For example, a roll number may encode the admission year, the department, the student category, the type of program, a serial number. For example, a roll number may look like 14-CS-90 2-P-01. The first part may represent the admission year. The CS part may represent the department. Another part may represent whether the student is undergraduate, postgraduate, or research student. The final digits may represent the serial number. So a roll number is not just a random identifier. It also carries meaning. It is a compact representation of multiple attributes. Instead of storing all these separately, they are encoded into one value. A key can be simple or composite. A simple key has only one attribute. Example, roll number. A composite key has multiple attributes. Example, first name plus last name. Now let us discuss foreign keys. A foreign key is an attribute that is a key in another table. For example, there is a student table. The student table has roll number as the primary key. There is a course table. The course table has course number as the primary key. There is an enrollment table. The enrollment table connects students and courses. The enrollment table stores which student takes which course. The roll number in the enrollment table refers to the student table. The course number refers to the course table. These are foreign keys. Now we move to relational query languages. After creating tables, we need a way to ask questions from the database. There are two main styles: procedural, declarative. Procedural means you describe how to get the answer. Most programming languages like C, C++, Java, and Python are procedural. You write the steps. For example, finding a square root. A procedural method says, start with a guess. Improve the guess. Check the error. Repeat until the answer is accurate. It tells us the method. It tells us how to calculate. Declarative means you only describe what you want. You do not specify the steps. For square root, a declarative statement would be find a number m such that m squared equals n. You describe the desired result. The system decides how to find it. Database query languages usually follow the declarative style. The user says what information is required. The database system decides the best way to retrieve it. Some important relational query models are relational algebra, relational tuple calculus, relational domain calculus. These concepts allow us to work with relational databases. One more important point: these queries languages are not Turing complete. This means they are not designed to perform every possible computation like a general programming language. They are specialized for working with relational data. This completes the introduction to the relational model. We learned what attributes are, what domains are, what schema and instances mean, what keys are, what primary keys, candidate keys, and foreign keys are, and how relational query languages work. The next module will continue with more concepts. Thank you.
Introduction. Welcome to Module 7 of the Database Management Systems course in IIT Madras BSc online program. In the last module, we started discussing the specific details of the relational model. We introduced the basic notions of attributes, their types, relational schema, relational instances, and keys with their different categories. We also briefly discussed the languages that a relational system uses. In this module, we will continue with relational algebra. We will understand the first language used for handling queries in relational databases. We will study its operators in greater depth. Module objectives. The main objective of this module is to understand relational algebra operators in detail. Relational operators. Before discussing the operators, remember one important thing. A relation is a set. Because a relation is a set, the ordering of elements, or the ordering of rows and tuples, does not matter. For example, suppose we have a relation with attributes A and B. It has 4 tuples: A1, B1, A1, B2, A2, B1, A2, B2. If the same tuples are written in a different order, the relation is still the same. The instances are equivalent because sets do not have ordering. Second, a set must always contain unique elements. Therefore, all rows and tuples in a relation must be distinct. If a row appears twice, it is not a valid relation. Only one copy of that row should exist. Keep these 2 rules in mind while studying relational algebra operators. Select operation. Selection of rows. The first operation is called select. As the name suggests, select operation chooses a subset of rows from a relation which satisfy given condition. The select operation is represented using the Greek letter sigma. After sigma, we write a boolean condition. This condition decides which tuple should be selected. Then we write the name of the relation. For example, suppose we have a relation R. We want to select rows where R is equal to B. and also D is greater than 5. First, check the condition are equal to B. Only rows where R and B have the same value survive. After that, apply the second condition. D must be greater than 5. Rows failing this condition are removed. Finally, only the tuples satisfying both conditions remain. This is because the condition uses AND. If instead we used OR, the condition would be are equal to B or D greater than 5. In OR, a tuple survives if it satisfies even one condition, so more rows will be selected. In some cases, the whole relation itself may be selected. Selection is therefore a horizontal operation. It selects rows. Projection operation. Selection removed rows. Projection removes columns. Projection is written using the Greek letter pi. After pi, we write the columns we want to keep. Any column not mentioned is removed. For example, if a relation is columns A, B, and C, and we perform projection on A and C, column B is removed completely. After removing B, duplicate rows may appear. But remember, a relation is a set, so duplicate rows cannot exist. Therefore, duplicate tuples are removed. For example, if after projection we get alpha 1, beta 1, alpha 1, beta 1, alpha 1, beta 2, the repeated tuple is deleted. The final relation contains only unique tuples. Projection is therefore a vertical operation. It selects columns. Union of two relations. The next operation is union. Union is a normal set operation. Two relations can be combined using union only if they have the same attributes. The number of columns and their domains must match. When we perform union, all tuples from the first relation and all tuples from the second relation are combined. After combining, duplicate tuples are removed. This is because the result must still be a set. Set difference of two relations. Difference is another set operation. The difference R minus S means all tuples that are present in R but not present in S. So we remove from R all tuples that also exist in S. For example, if R contains 5 tuples and S contains 2 of those tuples, the result contains the remaining 3 tuples of R. Intersection of two relations. Intersection gives the tuples common to both relations. A tuple appears in the intersection only if it exists in both relations. Intersection and difference are related. Intersection can be created using difference. For example, R minus S gives tuples only in R. Then removing those from R again leaves the common tuples. This is basic set algebra. Cartesian product. Cartesian product combines two relations. It takes every tuple from the first relation and pairs it with every tuple from the second relation. For example, if the first relation has 2 tuples and the second relation has 4 tuples, the Cartesian product will have 2 multiplied by 4, which gives 8 tuples. Every possible pairing is created. The result contains all possible combinations of rows. Cartesian product naming issue. There is a small problem. Suppose both relations have a column with the same name. The result cannot have 2 attributes with exactly the same name, so we rename them temporarily. For example, R.B and S.B. Now they are different attributes. The relation name is added before the attribute name to avoid confusion. Renaming a table. Sometimes we need to rename a relation itself. This is especially useful when performing Cartesian product of a relation with itself. Suppose we want R cross R. Both copies have the same attribute names, so we rename one copy. For example, call it S. Then we can perform R cross S. This avoids naming conflicts. Composition of operations. Relational algebra operators can be combined. We can apply multiple operations one after another. For example, first perform Cartesian product, then apply selection, then apply projection, The output of one operation becomes the input of another. This allows complex queries to be written. Continued in next message with natural join and aggregate operators. OK, continuing. Natural join. Natural join is a special operation in relational algebra. It combines two relations based on common attributes. Suppose we have two relations R and S. The result of natural join contains attributes from both relations. The first step is similar to Cartesian product. We combine tuples from both relations. But there is an extra condition. If R and S have common attributes, only tuples where the common attributes have equal values are kept. In Cartesian product, every possible combination is allowed. In natural join, only matching combinations are allowed. For example, suppose relation R has attributes A, B, C, D, and relation S has attributes B, D, E. The common attributes are B and D. During natural join, a tuple from R is combined with a tuple from S only if the value of B is the same in both, and the value of D is the same in both. If the values do not match, that combination is removed. After this matching is done, the duplicate columns are removed. Because the common attributes are already identical, there is no need to keep two copies. So natural join can be understood as, first, perform Cartesian product. Then select rows where common attributes match. Then remove duplicate common columns. Natural join is a very powerful operation. It is used frequently in database queries. Aggregate operators. Besides relational operators, there are aggregate operators. Relational operators always take one or two relations as input, and they always produce a relation as output. Examples: select, project, union, intersection, difference, Cartesian product, natural join. Aggregate operators are different. They take a relation, perform calculations on one or more columns, and usually produce a single value. For example, suppose we have a table with a column B. We can perform sum of B, maximum value of B, average value of B, minimum value of B, count of values. These operations combine many rows into one result. For example, if column B contains 1, 2, 3, 4, the sum operation gives 10. The maximum operation gives 4. The output is not a table. It is a single value. Another example. Suppose we first select only rows where B is greater than 2. Then perform sum on B. The selection gives a smaller relation. The aggregation then calculates the sum of that smaller relation. So the difference is relational operators deal with tuples and relations. They always produce relations. Aggregate operators perform calculations. They usually produce one value. Aggregate operators are not part of pure relational algebra, because relational algebra mainly deals with relations. But they are very useful in practical query languages like SQL. Notes about relational languages. Every query takes tables as input and produces tables as output. The data in the output table must come from the input tables. Relational algebra is not Turing complete. This means there are some computations that cannot be expressed using only relational algebra. For such tasks, we need a normal programming language. Summary of relational algebra operators. The important relational algebra operators are select, used for choosing rows, projection, used for choosing columns, union, combines two compatible relations, difference, finds tuples present in one relation but not another, intersection, finds common tuples, Cartesian product, creates all possible combinations of tuples, natural join, combines relations based on matching common attributes, aggregate operators, perform calculations like sum, average, maximum, minimum, and count. Module summary. In this module, we introduced relational algebra and studied its basic operators. These operators form the foundation for querying relational databases. Thank you for your attention. We will continue this topic in the next module.
Part 1. Welcome to Module 8 of the Database Management Systems course in the IIT Madras online BSc program. Before this module, we introduced the basic overview of the relational database system. We defined basic terms such as attributes, keys, different types of keys like superkeys, candidate keys, and foreign keys. We also discussed relational schema and relational instances. We saw that there are two main parts of a language used to work with a database application system. The first is data definition language, abbreviated as DDL. The second is data manipulation language, abbreviated as DML. The language SQL, originally called structured query language, can perform both of these tasks. In this module, we will build upon the relational query language, especially SQL, and understand its basic structure. The three main topics we will discuss are: first, the history of SQL; second, data definition language; third, data manipulation language. History of SQL. Before learning something new, it is useful to look at its history. SQL started as structured English queries language. It was developed by IBM at their San Jose Research Laboratory as part of the System R project. This work happened in the late 1970s and early 1980s. Later, it was renamed Structured Query Language. However, the original pronunciation, SQL or SQL, continued to be used. Since any language used globally needs standardization, several standardization efforts started. The first major standard was SQL ASCII. This was made an American standard by the American National Standards Institute, also called ANSI. In 1989, integrity constraints were added. Integrity constraints are rules that ensure data remains correct and consistent. The major change came in SQL 92. This became the first international ISO standard. ISO stands for International Organization for Standardization. The standard number was ISO 9075. After this, SQL became an industry standard. Different versions of SQL continued to appear. Some versions added major features. SQL 1999 was an important version. It added many useful features. These included regular expression matching. Regular expressions are patterns used to search and match text. Recursive queries. Recursive queries allow a query to repeatedly use its own result to solve problems. For example, finding all levels of a hierarchy. SQL 1999 also added support for triggers. A trigger is an automatic action that runs when a certain database event happens. For example, automatically updating a record when another record changes. It also added support for procedural and control statements. Normally, SQL is a declarative language. This means we tell the database which result we want, not exactly how to calculate it. However, procedural features allow some step-by-step logic. SQL 1999 also added arrays and structured data types. Another important feature was embedding. Embedding means combining SQL with a normal programming language. For example, SQL can be embedded inside Java. This is called SQL GRT. Java can also be embedded inside SQL. This allows developers to decide which parts of the task should be handled by database operations and which parts should be handled by normal programming. SQL 2003 added another major feature. It added support for XML. XML stands for Extensible Markup Language. It is a standard format for exchanging information between systems. Later, SQL 2006 added complete XML functionality. This included importing XML data, storing XML data, manipulating XML data, exporting and publishing XML data. After this, many smaller updates continued. The latest versions of SQL continued adding improvements. SQL Standard Compliance. SQL became the practical standard for relational databases. Almost every relational database system uses SQL. However, not every database follows every SQL standard completely. Some systems fully support certain standards. Others support only parts of multiple standards. Most commercial databases support SQL 9.2. Many also support features from SQL 2003 and SQL 2006. Because of these differences, the exact syntax may vary between database systems. A query written for one database system may need small changes for another system. This is true for both commercial and open source databases. Alternatives to SQL in programming languages. We have many choices. For example, we can use C++, Java, Python, and other languages. We choose based on our application. However, for relational databases, SQL has no real competitor. There were some alternative query languages, such as SQL. SQL was based more on relational calculus ideas. But practically, SQL dominates relational databases. Many programming languages have front-end libraries that make SQL easier to write. Examples include interfaces for languages such as Lisp, .NET, Ruby, Haskell, and Scalar. These are not replacements for SQL. They are mainly ways to use SQL from different programming environments. Languages derived from SQL. Many languages have been inspired by SQL. One important example is Sparkle. Sparkle stands for Sparkle Protocol and IDF Query Language. The acronym itself is interesting because it contains the word Sparkle again. Sparkle is a query language used for RDF. RDF stands for Resource Description Framework. Instead of tables, RDF stores information as triples. A triple contains a subject, a predicate, an object. Sparkle is commonly used with graph databases. It was standardized by the World Wide Web Consortium, also called W3C. The current widely used version is Sparkle 1.1. Part 2 continues with data definition language, creating tables, data types, constraints, and SQL queries. OK, database management systems. Module 8 SQL Introduction, Data Definition Language, and Data Manipulation Language Part 2. Now that we have understood the history of SQL, let us move to the main part of the language. First, we discuss Data Definition Language, also called DDL. DDL is used to define the structure of the database. It allows us to define the schema, the relations or tables, the domains of attributes, and integrity constraints. Integrity constraints are rules that ensure the data stored in the database remains correct. SQL data types, just like programming languages such as Python, C, or C++, have different data types. SQL also has different data types. Some common SQL data types are character, variable character, integer, small integer, numeric, floating point, string. A character data type, written as char, stores a fixed number of characters. For example, char 5 means the field must contain exactly 5 characters. If you store only 3 characters, it is not considered valid. A variable character type, written as varchar, allows a variable number of characters up to a maximum limit. For example, varchar 5 allows values containing up to 5 characters. A value with 3 characters is also valid. Integer stores whole numbers. Small integer stores smaller whole numbers. Numeric allows numbers with a specific precision. Precision means the total number of digits. The number of digits after the decimal point is called scale. For example, numeric 82 means the total number of digits can be 8. 2 digits can appear after the decimal point. So a value like 72,396.50 is valid. Creating a table. A database table is created using the create table command. To define a table, we must specify the table name, the attribute names, the order of attributes, the data type of each attribute, and the constraints. For example, consider an instructor table. We write create table instructor. The first attribute is ID. The type of ID is char5. This means the ID contains 5 characters. The next attribute is name. The name does not have a fixed length, so we use varchar20. This means the maximum length is 20 characters. The department name is also varchar20. The salary is stored as numeric 82. This allows a salary with up to 8 total digits and 2 digits after the decimal point. Integrity constraints defining attributes is not enough. We also need to define rules about the data. These rules are called integrity constraints. One important constraint is not null. Not null means a value must be provided. The field cannot be empty. For example, instructor name should not be missing. Another important constraint is primary key Y. A primary key uniquely identifies every row in a table. A primary key must always be unique. It also automatically becomes not null. This is because a missing value cannot uniquely identify a record. Another constraint is foreign KY. A foreign key connects one table with another table. For example, the instructor table may contain a department name. That department name must already exist in the department table. If the department table does not contain a department called aerospace, then an instructor cannot have aerospace as the department value. This maintains consistency between tables. Example of student table: consider a student table. It may contain student ID, name, department, total credits. The student ID is the primary key. The name is not null. The department is stored as a variable character value. Total credits is a numeric value without a decimal part. The department attribute may also be a foreign key referring to the department table. The same ideas apply to other tables like courses and tags. Other table operations. SQL also allows modifying tables. The delete command removes rows from a table. For example, delete from students. This removes all rows from the students table. The drop table command removes the entire table. This removes the table structure itself from the database. The alter table command modifies the structure of an existing table. For example, we can add a new attribute, remove an existing attribute. Changing a table structure affects existing data. If we remove an attribute, existing records lose that attribute value. If we add a new attribute, existing rows initially have no value for it. Therefore, the new attribute will usually contain null values until updated. Data manipulation language. Now we move to data manipulation language, also called DML. DML is used for querying and modifying data. The basic SQL query structure is select from where. This is called the select from where structure. Select clause specifies which attributes we want in the output. It is similar to the projection operation in relational algebra. For example, select name from instructor. This means take the instructor table, extract the name column, return that column as the result. SQL keywords are usually case-insensitive. This means select, and select are treated the same. Duplicate values in SQL relational algebra follow set theory. Sets do not allow duplicate values. However, SQL normally allows duplicates. For example, if many instructors have the same name, selecting names may show the same name multiple times. If we want to remove duplicates, we use distinct. Example, select distinct department name from instructor. This returns each department name only once. If we want all values including duplicates, we can use all. All is the default behavior. Selecting all attributes, the symbol star means all attributes. So, select star from instructor means return every column of the instructor table. Using constant values, SQL can also return fixed values. For example, select 423. This produces a result containing the value 423. We can also give it a name. For example, select 423 as code. The output column will be called code. Performing calculations. SQL can perform calculations inside select. For example, select ID, name, salary divided by 12 from instructor. This takes the salary value and divides it by 12. The result can be renamed. For example, salary divided by 12 as monthly salary. This creates a new output column called monthly salary. Part 3 continues with where clause, from clause, joins, Cartesian products, and final summary. OK, database management systems. Module 8 SQL Introduction, Data Definition Language, and Data Manipulation Language. Part 3 where clause. The where clause is used to specify conditions. It acts as a filter. The condition in a where clause is called a predicate. A predicate is a boolean condition. A boolean condition can have two results, true, false. Without a where clause, SQL returns all rows. For example, select name from instructor. This returns the names of all instructors. But if we write select name from instructor where department name equals computer science, then only instructors belonging to the computer science department are returned. This is similar to the selection operation in relational algebra. The select clause corresponds to projection. The where clause corresponds to selection. Conditions can also be combined. For example, select name from instructor where department name equals computer science and salary is greater than 80,000. This returns only instructors who satisfy both conditions. We can use logical operators like and, or, not to create more complex conditions. From clause. The from clause specifies the tables that are used in a query. It defines the scope of the query. A query must have at least one table. For example, select name from instructor. Here, instructor is the table in the from clause. The name attribute comes from that table. Using multiple tables, the from clause can contain multiple tables. For example, select star from instructor, teaches. When multiple tables are written together, SQL first creates a Cartesian product. A Cartesian product means every row from the first table is combined with every row from the second table. Suppose instructor has 5 rows and teaches has 5 rows. The Cartesian product creates 25 combinations. Every possible pairing is created. Why Cartesian product alone is not useful? A Cartesian product often creates meaningless combinations. For example, an instructor may appear connected to courses they do not actually teach. So we need a condition. Suppose both tables contain an ID attribute. The instructor table has instructor ID. The teacher's table also has instructor ID. If these ID are equal, it means this instructor teaches this course. So we add a where condition. Example, select star from instructor, teaches, where instructor ID equals teacher's ID. Now the result becomes meaningful. The query keeps only matching rows. This process is the basis of joining tables. Connection with relational algebra. Many SQL operations directly correspond to relational algebra. Select attributes. This is projection. Where condition. This is selection. From multiple relations, this creates a Cartesian product. Additional conditions. These filter the product and create useful joins. Module summary. In this module, we introduced SQL. We discussed the history of SQL. Different SQL standards. SQL data types. Data definition language. Creating tables. Integrity constraints. Primary keys. Foreign keys. Modifying table structures. Data manipulation language. The basic SQL query structure. Select. From. Where. We saw that SQL is a declarative query language. It tells the database what result is required rather than explaining the exact steps to calculate it. SQL has become the standard language for relational databases. In the next module, we will continue with more advanced SQL concepts and queries. Thank you.
Hello everyone. In this particular video, we're going to discuss and execute the code that we discussed in Lecture 2.3. First, let's look at the slides from Lecture 2.3. We discussed the DDL command, which means Data Definition Language. As you all know, SQL is used to retrieve data from a database. In SQL, we store data in a tabular format, which means a structured format. For example, if we have a table called student, it will contain columns and rows. The columns could be roll number, name, age, department. The data is stored according to these columns, and every row represents one record. In DBMS, columns are called attributes. So whenever we say attribute, it means a column name of a table. Whenever we say student relation or student table, both mean the same thing. Similarly, rows are also called tuples. So attributes are columns. Tuples are rows. A relation is a table. This is how data is stored in a relational database. Now, when we create or define a table, we need to know some things. First, we need to know the attribute names. Second, we need to know what type of data each attribute can store. This is called a data type. Third, we need constraints. A constraint means a restriction that we apply on a column so that it can only accept certain values. So for creating a table, we need to understand data types, constraints, and attributes. Let's discuss data types in SQL. SQL provides different domain types or data types. Some common data types are character, variable character, integer, small integer, numeric, real, double precision, float. Character and variable character are used for storing string values or text. For example, names or department names. Integer is used for storing whole numbers. Small integer is used for smaller range integer values. Numeric is used for decimal values. For example, if we write numeric 3, 1, it means the total number of digits allowed is 3, and only one digit is allowed after the decimal point. So values like 44.5 or 4.5 are valid. But values like 4.50 are not valid because there are 2 digits after the decimal point. Similarly, 444.5 is not valid because the total number of digits becomes more than 3. So numeric defines the precision and scale of decimal numbers. Now we also have real, double precision, and float data types. These are used for storing floating point numbers. Now let's look at the university database schema. Throughout Week 2 and Week 3, we will discuss SQL using the university database. The dataset has already been provided. You can load it into pgadmin. A schema diagram represents tables and their relationships. For example, student is a relation. It has attributes ID, name, department name, total credit. Another relation is takes. It contains ID, course ID, section ID, semester, year, grade. These tables are connected using common attributes. The arrows in the schema represent relationships between tables. Now let's discuss how to create a table. When we say create a table, we're creating a relation in SQL. The syntax is create table. Then we write the table name. For example, create table student. After that, we specify attributes and their data types. An attribute is the column name. The data type tells what kind of values that column can store. For example, consider the instructor table. We write create table instructor. Then we define ID, name, department name, salary. ID can have a character type with length 5. Name can have a variable character type. Department name can also have variable character type. Salary can have numeric type with precision. For example, numeric 8, 2. This means 8 digits are allowed in total. 2 digits are allowed after the decimal point. So a value like 70 2396.50 is valid. At this stage, we are only creating the table. No constraints are applied yet. Now let's execute this in SQL. First, we create a database. Then we open the query tool. We write the create table command. After executing it, the table is created successfully. To verify it, we use select star from instructor. Here, star means all attributes or all columns. Since we have not inserted any data, the table has columns, but no rows. This is how we create a table in SQL. Part 2 continues with constraints, primary key, foreign key, insert, delete, select queries, reclose, and joins. OK, part 2. Now let's discuss constraints in SQL. Constraints are rules that restrict what values can be stored in a table. Some common constraints are not null, unique, check, primary key, foreign key. Not null means that a column cannot have an empty value. For example, if a name column is marked as not null, then every record must have a name. A primary key is a special constraint. A primary key means that the attribute must have unique values, and it cannot contain null values. So primary key is basically not null plus unique. For example, in the instructor table, ID is the primary key. Every instructor must have a unique ID. Now let's understand a foreign key. A foreign key is an attribute that refers to another table. For example, in the instructor table, department name refers to the department table. This means that any department name entered in the instructor table must already exist in the department table. For example, if the department table does not contain aerospace, we cannot insert aerospace as a department name in the instructor table. This maintains consistency between tables. Now let's create the instructor table with constraints. The syntax looks like create table instructor. Then we define ID, name, department name, salary. We add the not null constraint on name. Then we specify primary key ID. This makes ID unique and not null. Then we specify foreign key department name references department. This means department name will take values only from the department table. Let's try to execute this. If we try to create the table again, we get an error because the instructor table already exists. So first, we need to remove the existing table. We use drop table instructor. This deletes the table completely. Now if we try creating instructor again, we get another error. The reason is that the department table does not exist yet, because instructor depends on department through the foreign key. So first we need to create the department table. Looking at the schema, the department table has department name, building, budget. The underlined attribute represents the primary key. So department name is the primary key. Let's create it. Create table department. Department name is variable character. We make department name the primary key. Building is variable character. Budget is an integer. After execution, the department table is created. Now we can create the instructor table. After creating it, we can see the primary key symbol in pgadmin. This shows that ID is the primary key, and department name is the foreign key. Now we can create other tables. For example, student table, course table. But some tables depend on others. For example, the section table depends on the classroom table. The text table depends on the section table. So the reference tables must be created first. Now let's discuss inserting data. Until now, we only created empty tables. To add data, we use the insert command. The syntax is insert into table name, values. Then we provide the values. For example, insert into instructor, values, ID, name, department, salary. If we try inserting an instructor before adding the department, we get a foreign key error because the department does not exist. So first we insert data into the department table. For example, department name, biology. Building size. Budget. Now the department exists. We can insert the instructor with department biology. The insertion is successful. To view the data, we use select star from department or select star from instructor. This displays all rows and columns. This is how rows are added into tables. Now let's discuss deleting data. The delete command removes rows. For example, delete from student. This removes all rows from the student table. If we want to remove only specific rows, we add a condition. For example, delete from student, where roll number equals a particular value. This deletes only matching records. The drop table command removes the entire table. The alter command modifies the structure of a table. For example, adding a new attribute, removing an attribute, changing the schema. Now let's move to DML. DML means data manipulation language. The basic SQL query structure is select, from, where. Select specifies which attributes we want. From specifies the table. Where specifies the condition. For example, select name from instructor. This gives all instructor names. The name of the attribute is case insensitive, so name and name are treated the same. SQL also allows duplicate values in query results. For example, if multiple instructors have the same name, all names will appear. If we want only unique values, we use the keyword distinct. Example, select distinct department name from instructor. This removes duplicate department names. The keyword all means keep duplicates. By default, SQL keeps duplicates. Now let's discuss the star symbol. Select star from instructor means select all columns from instructor. It displays every attribute. An attribute can also be a literal value. For example, select 437. This simply returns the value 437. We can also rename the output column. Example, select 437 as F. Now the column name becomes F. We can perform arithmetic operations inside select. For example, select ID, name, salary divided by 12. This calculates monthly salary. We can rename it as monthly salary. This rename only affects the output. It does not change the original table. Part 3 continues with where clause and slash or conditions and Cartesian product. OK, part 3. Now let's discuss the where clause. The where clause is used to apply conditions. Without a where clause, select name from instructor will give all instructor names. But if we write select name from instructor where department name equals computer science, then we only get instructors who belong to the computer science department. The where clause filters the rows. The condition inside where gives either true or false. We can also use multiple conditions. For example, select name from instructor where department name equals computer science and salary is greater than 80,000. This will return only instructors who satisfy both conditions. The logical operators are and, or, not, and means all conditions must be true. For example, department is computer science and salary is greater than 81,000. Only rows satisfying both conditions are returned, or means at least one condition must be true. For example, department is computer science, or salary is greater than 81,000. This will return instructors from computer science, and also instructors from any department whose salary is greater than 81,000. Now let's discuss the from clause. The from clause tells SQL which tables we're using. So far, we were using one table. For example, select star from instructor. But we can also use multiple tables. Example, select star from instructor, teaches. When multiple tables are written together, SQL performs a Cartesian product. A Cartesian product means every row of the first table is combined with every row of the second table. For example, if instructor has 10 rows, and teaches has 5 rows. The result will have 10 multiplied by 5, which means 50 rows. This creates all possible combinations. Usually, a Cartesian product alone is not very useful. We normally add a condition to connect related rows. For example, instructor ID and teacher's ID. When the ID match, we get meaningful information about which instructor teaches which course. This is how SQL combines information from multiple tables. So in this lecture, we discussed data definition language, creating tables, data types, constraints, primary keys, foreign keys, insert command, delete command, drop table, alter command, and basic data manipulation language. We also discussed the basic SQL query structure select, from, where, select chooses columns, from chooses tables, where applies conditions. This completes the introduction to SQL commands and queries. Thank you.
Hello everyone, I am P, your course instructor for the Database Management System course. In this video, we're going to discuss how to create tables, what different data types are, and what constraints we have in SQL, which stands for Structured Query Language. The focus will be mainly on the content given in our syllabus. I will also suggest some resources so that you can explore this topic further. Let us go to pgadmin now. I hope everyone has installed pgadmin and loaded the databases. Here you can see I'm using PostgreSQL version 14. You can use any version above 14. Here I already have different databases created. But if you want to create a new database, you simply right-click on Databases, then select Create, and then select Database. Now we need to give a name. For example, I'm giving the name SQL ITM. The database name depends on you. You can give any name. Then click on the Save button. Now on the left-hand side, you can see that the database named SQL ITM has been created. Now we want to use this database. To do that, right-click on the database name. Here you can see the Query Tool option. Click on Query Tool. This is the interface where we can write queries. This is the Run button, and this area shows the output. Now let us understand the syntax for creating a table. First, we write the create command. Then we specify what we want to create. In this case, we want to create a table. So we write create table. After that, we specify the table name. Whatever table name we want to give, we mention it here. Then inside brackets, we specify the attributes. A database consists of different tables that are linked with each other. A table consists of rows and columns. Here, attribute means the column name of a table. So when we say attribute, we're talking about the column name. For every column, we need to specify the column name along with its data type and constraint. Constraint is an optional part, but the data type is mandatory for every column. So the basic syntax is create table. Then specify the table name. Inside brackets, specify the column name, data type, and constraint. This process is repeated for every column. For example, if a table has 3 attributes, then all 3 attributes need their column names and data types. Constraints are optional. The mandatory part for creating a table is the column name and its data type. Now let us discuss different data types. I am focusing only on the data types mentioned in our course. There are other data types also, which you can explore. The first data type is character, also called char. It stores characters with a fixed size. The second is varchar, which means variable character. It stores characters with a variable length. The third is date. The date data type is used for storing dates. The fourth is integer, also called int. It stores whole numbers. The fifth is boolean. Boolean stores either true or false values. These are the common data types we generally use: character, varchar, date, integer, and boolean. Now let us discuss constraints. Constraints are rules applied to columns to maintain data accuracy. The first constraint is not null. The second constraint is unique. The third constraint is check. The fourth constraint is primary key. We also have a foreign key constraint. A primary key is used to uniquely identify each record in a table. We will discuss foreign keys later. These are the important data types and constraints. Remember that data types and constraints are not case sensitive. You can write them in capital letters or small letters. Now let us see how to create a table. I'm going to create a table called student. The command is create table student. Inside this table, we will add some attributes. The first attribute is roll number. Roll number can contain alphanumeric values, meaning numbers and letters. So we use varchar. For example, varchar with size 10. We apply the primary key constraint to roll number. The next attribute is name. For name, we can use the character data type. We can set the size as 10. We apply the unique constraint on the name. The next attribute is date of birth. For date of birth, we use a date data type. We apply the not null constraint because date of birth should always have a value. The next attribute is age. Age uses the integer data type. We also apply not null because age should not be empty. The last attribute is active. This tells whether a student is active in the course or not. For this, we use the boolean data type because the value can be either true or false. So this table contains different data types and constraints for demonstration. Character stores strings. Varchar also stores strings, but the difference is in storage. Character uses fixed storage. Varchar uses variable storage. For example, if a character column has size 10, even if we store only 3 letters, the remaining space is filled. But varchar only uses the required amount of storage. Date data type is used for dates like date of birth or joining date. Integer stores whole numbers. Boolean stores true or false values. Now we have created the student table with roll number as primary key, name with unique constraint, date of birth with not null constraint, age with integer and not null, active with boolean. Now let us execute the query. Click the Run button. The Create Table query is executed successfully. The student table has been created. To view the table, go to the database. Open Schemas. Open Public Schema. Open Tables. You can see the student table with the columns we created. Now let us view data from the student table. We use the select command. Select all columns from student. The star symbol means all columns. Since the table is empty, no rows are displayed. Part 2 will continue from inserting records and explaining varchar, char, primary, key, unique, not null, and check constraints. Okay, part 2. Now we want to insert a row or record into the student table. For inserting data, we use the insert command. The syntax is insert into table name. Then we specify values. For example, insert into student. Then we provide the values. If we do not specify column names, the values must be given in the exact same order as the columns were created. For example, first we give the roll number. Since roll number uses varchar data type, we use quotation marks. Next, we give the name. Since name is also character type, it is written inside quotation marks. Next is date of birth. Since it is a date value, it is written in date format. Next is age. Since age is an integer, we directly write the number without quotation marks. The same applies to Boolean values. For Boolean, we use values like true or false. Now we execute the query. The record is successfully inserted. To check the data, we again use select all columns from student. Now we can see the inserted record. This is how we insert records into a table. Now let us understand data types one by one. First, let us discuss varchar. Earlier, we created roll number as varchar with size 10. What happens if we insert more than 10 characters? For example, if we try to insert a value longer than 10 characters, the database gives an error. It says the value is too long for the character varying type. The database does not automatically remove extra characters. Instead, it rejects the value. This helps maintain data integrity. It prevents incorrect data from entering the database. Now let us discuss character data type. Character also has a size limit. If the size is 10, we cannot insert more than 10 characters. It will also give an error. The difference between character and varchar is storage. Character uses fixed storage. Varchar uses variable storage. In character type, even if we store fewer characters, the remaining space is filled with empty spaces. For example, if a character column has size 10 and we store only 3 characters, the database still reserves space for 10 characters. But varchar stores only the actual characters. Because of this, varchar is usually more storage efficient. You may wonder why we need character when varchar exists. Character is useful when the length is always fixed. For example, some identification numbers like passport numbers, certain codes, or fixed length values. For these cases, character can be used. Now let us discuss date data type. Date is used for storing dates like date of birth or joining date. The database can accept date formats depending on the database system. Now integer data type. Integer stores whole numbers. For example, age can be stored as an integer. Boolean data type stores only true or false values. If we try to insert any random text into a Boolean column, the database gives an error. Boolean accepts only valid Boolean values like true or false. Now let us discuss constraints. The first important constraint is primary key. A primary key uniquely identifies each row in a table. A primary key is a combination of 2 properties, not null and unique. Not null means the value cannot be empty. Unique means duplicate values are not allowed. For example, roll number is a primary key. 2 students cannot have the same roll number. Also, roll number cannot be empty. If we try to insert the same roll number again, the database gives an error. It says that the duplicate value violates the primary key constraint. Now let us discuss the unique constraint. A unique constraint prevents duplicate values in a column. For example, if the name column has a unique constraint, 2 students cannot have the same name. If we try to insert a duplicate name, the database rejects it. Now let us discuss the not null constraint. Not null means the column must have some value. For example, date of birth is marked as not null. If we try to insert a student without a date of birth, the database gives an error. It says that the null value violates the not null constraint. So not null ensures that important fields always contain data. If we do not apply any constraint to a column, the column can contain null values. Null means no value is provided. For example, if the active status column has no constraint, we can leave it empty. The database will allow the null value. By default, columns allow null values unless we specify otherwise. Now the last constraint is check. The check constraint is used to enforce a condition. For example, we can say, age must be greater than 18. Now whenever we insert a student record, the database checks this condition. If someone tries to insert a student with age less than 18, the database rejects it. The check constraint prevents invalid data. So in this tutorial we learned how to create a table, different data types in SQL, character, varchar, date, integer, boolean, and constraints, not null, unique, check, primary key, foreign key. These constraints help maintain accuracy and integrity of data in the database. There are many more data types and constraints available in PostgreSQL. You can explore them in PostgreSQL documentation. Thank you.
Hello everyone. I am P, instructor for the Database Management System course. In this tutorial, we're going to discuss DDL commands. DDL stands for Data Definition Language. When we say data definition language, it means commands used to define the structure of a database. All commands that deal with the structure of a database come under DDL. Structure means things like the table name, the column names, and all metadata related to columns. If we want to make changes to this structure, we use DDL commands. Let us discuss these commands one by one. We will use pgadmin to understand DDL commands. The 5 DDL commands we will discuss are create, alter, drop, truncate, and rename. We already discussed the create command in the previous tutorial for creating tables. Let us quickly revise it. The create command is used to create a new database object. For example, a table. We can also create a database using this command. For example, create database. Then specify the database name. This creates a new database with that name. We can also create views using the create command. Now let us see the syntax for creating a table. We write create table, then specify the table name. Inside brackets, we specify the column names, their data types, and constraints. Constraints are optional, but column names and data types are mandatory. We already discussed data types and constraints in the previous tutorial. For example, we can create a table called employees. The employees table can have columns like employee ID, first name, last name, and age. Employee ID can have an integer data type and a primary key constraint. First name can have varchar with size 50. Last name can have varchar with size 50. And age can have an integer data type. If you observe, the first name, last name, and age columns do not have any constraints. This means they can contain null values. They can also contain duplicate values. If we do not specify any constraint, the database allows null values and duplicate values. Now let us execute this command. The table is created successfully. To check the table, we use the select command. Select all columns from employees. Now we can see the employees table with the 4 columns. This is how we create a table in SQL. We specify the column name and its data type. If we want restrictions, we add constraints. Now the second DDL command is alter. The alter command is used to modify the structure of an existing table. Suppose a table is already created, but now we want to change something. For example, add a new column, delete a column, modify a column, or add a constraint. For these changes, we use the alter command. First, let us see how to add a column to an existing table. The syntax is alter table. Then specify the table name. Then use add. After that, specify the new column name and data type. For example, we want to add a salary column to the employees table. We write alter table employees. Add salary. The salary data type can be decimal. For example, decimal 10,2. This means the total number of digits allowed is 10. Out of those 10 digits, 2 digits can be after the decimal point. So a value can have 8 digits before the decimal point and 2 digits after it. Now execute the command. The salary column is added successfully. If we check the employees table again, we can see the salary column. This is how we add a column to an existing table using the alter command. We can also remove a column using alter. The syntax is alter table. Specify the table name, then drop column, then specify the column name. For example, alter table employees, drop column salary. This removes the salary column from the employees table. The command executes successfully. Now if we check the table again, the salary column is removed. So alter can be used to add or remove columns from an existing table. Part 2 continues with drop, truncate, delete, and rename commands. Okay, I'll convert it into the same audio-friendly transcript style. I'll remove timestamps, expand symbols / short forms, add natural pauses, and explain shorthand terms as they appear. Hello everyone. I'm P, your course instructor for the DBMS course. In this particular tutorial, we're going to discuss DDL commands. DDL means Data Definition Language Commands. Okay, so what are DDL commands? When I say Data Definition Language, it means we're defining the structure of a database. All those commands which deal with the structure of a database are called Data Definition Language Commands. When I say structure, it means things like table names, column names, and all the metadata about the columns. Metadata means information that describes the data, such as column names, data types, and constraints. So if we want to make any changes in the structure of a database, we use DDL commands. Okay, let us discuss them one by one. Let us go to pgadmin and discuss these DDL commands. In this tutorial, we're going to discuss 5 commands. They are create, alter, drop, truncate, and rename. We already discussed the create command in the previous tutorial for creating a table. Let us quickly revise it. The first command is the create command. The create command is used to create a new database object. A database object can be a table, a database, or a view. A view is a virtual table created from the result of a query. We can also create a database using the create command. For example, we can write create database, then specify the database name. This will create a new database with that name. Now, what is the syntax for creating a table? We write create table, then we specify the table name. Whatever name we want to give to the table, we write it there. Inside brackets, we specify the column names, their data types, and constraints. Constraints are rules applied to columns. Constraints are optional, but the column name and data type are mandatory. We already discussed different data types and constraints in the previous tutorial. For example, we can create a table called employees. This table can have employee ID, first name, last name, and age. Employee ID can have an integer data type and a primary key constraint. First name can have a variable character data type with size 50. Last name can also have variable character data type with size 50. Age can have an integer data type. If we do not specify any constraint for a column, it means that column can contain duplicate values and null values. Null means no value is stored. Now, let us execute this command. The table is created successfully. If we want to see the table, we use the select command. We write select star from employees. The star symbol means all columns. This command displays all the data from the employees table. So this is how we create a table in SQL. We specify column names, data types, and if required, constraints. Now, the second command is the alter command. The alter command is used to modify the structure of an existing table. Suppose a table is already created, but we want to add a new column, delete a column, or modify a column. We can use the alter command. First, let us see how to add a column. The syntax is alter table, then specify the table name, then use add. After that, specify the new column name and its data type. For example, alter table employees, add salary. The salary column can have a decimal data type. Decimal 10,2 means the number can have a maximum of 10 digits. Out of those 10 digits, 2 digits can be after the decimal point. For example, 12,345,678.90. This has 10 digits in total, with 2 digits after the decimal. Now we execute the command. The salary column is successfully added to the employees table. So this is how we add a column to an existing table using alter. We can also delete a column using alter. The syntax is alter table. Specify the table name. Drop column. Specify the column name. For example, alter table employees. Drop column salary. This will remove the salary column from the employees table. The column and its data will be deleted. Now let us discuss the drop command. The drop command is used to delete a database object. A database object can be a table, index, view, or even a database. When we drop an object, it is permanently deleted. The data inside that object is also lost. So we must use the drop command carefully. The syntax is drop table. Then specify the table name. For example, drop table employees. This deletes the employees table completely. Now let us discuss the truncate command. The truncate command is used to remove all rows from a table. A row means a record in a table. Unlike the delete command, truncate does not allow conditions. For example, using delete, we can say, delete only the student whose roll number is this. But with truncate, all rows are removed. The table structure remains. The syntax is truncate table. Then specify the table name. For example, truncate table employees. This removes all records from the employees table but keeps the table for future use. Truncate is usually faster than delete because it does not remove rows one by one. Now let us discuss the delete command. The syntax is delete from. Then specify the table name. Then use where to specify the condition. For example, delete from student, where roll number equals 21F14. This deletes only the student whose roll number is 21F14. We use the roll number because it is a primary key. A primary key uniquely identifies every row. If we use age instead, multiple students may have the same age and multiple rows could be deleted. So for deleting a specific row, we usually use the primary key. Now the last command is rename. The rename command is used to change the name of an existing database object. We can rename a table or a column. Usually in PostgreSQL, rename is used.
Introduction. Welcome to Module 9 of the Database Management Systems course in the IIT Madras online b.sc program. In the last module, we started discussing relational query languages. The actual commercial language we introduced was SQL, which stands for Structured Query Language. We introduced the basic structure of creating tables and doing basic manipulation on the table schema. A schema means the structure or design of a database table. We also discussed the basic structure of a select from where query. You may not yet be completely comfortable with this. Later, after we introduce more parts of SQL, we will go through detailed examples so that you become more familiar with writing queries. Module objective. Continuing from the previous module, we will discuss several other features of the basic query structure. These features allow you to write different forms of queries and, in many cases, make writing queries easier. We will continue from the concept of Cartesian product that we discussed at the end of the previous module. These topics come under additional basic operations. Cartesian product. We observed that a Cartesian product combines two relations. For example, if we have two tables called instructor and teaches, the Cartesian product creates every possible combination of rows from the instructor table and every possible combination of rows from the teaches table. If we specify instructor and teaches in the from clause and use a wildcard in the select clause, which means selecting all columns, then SQL creates one large table. This table contains all columns from instructor, all columns from teaches, and every possible combination of records. If both tables have a column with the same name, SQL identifies them using the table name. For example, if both tables have a column called ID, then they are written as instructor.id and teachers.id. However, this result is usually not directly useful. The reason is that a Cartesian product blindly combines records. The actual information is divided between tables. The instructor table contains details about instructors. The teachers table contains information about which instructor teaches which course, but it only stores the instructor ID. Suppose we want to find the courses taught by a particular instructor, like Professor Srinivasan. We cannot answer this using only the instructor table because it does not contain course information. We also cannot answer using only the teachers table because it does not contain the instructor name. But if we combine both tables, we can find the answer. The problem is that a Cartesian product creates many meaningless combinations. For example, it may combine an instructor with one ID and a teaching record with a different instructor ID. Those combinations are incorrect. The useful records are the ones where the instructor ID in the instructor table matches the instructor ID in the teachers table. So we remove unwanted records using a condition. The condition is the instructor ID should be equal to the teacher's ID. This condition is written inside the where clause. After applying this condition, only the matching records remain. Now instead of selecting every column, we only select the columns we need. For example, we select the instructor name and the course ID. The output will show something like Srinivasan, CS 101, Srinivasan, CS 315. This tells us which courses Professor Srinivasan is teaching. If we also want the course name, we need to combine this with another table containing course information. That table is the courses table. This operation of combining related tables is called a natural join. Natural join is useful for combining information stored across multiple tables. You can join 2 tables, 3 tables, 4 tables, or more. However, joining more tables creates larger Cartesian products, and then many records have to be removed. Therefore, the order in which joins are performed becomes important. Example: finding courses taught by art department, instructors consider the query. Find the courses being taught by all instructors in the art department. The first condition in the where clause performs the basic natural join. The second condition ensures that the instructor belongs to the art department. The department information is already stored in the instructor table. We name operation using a sometimes when writing a select query. You may want to give a different name to a column or a table. For this, we use the keyword as. For example, suppose we perform a Cartesian product of the instructor table with itself. This creates a problem. Both copies of the table have columns with the same names. For example, both have an ID column. SQL cannot know which ID we mean. Another problem occurs when comparing values between the 2 copies of the same table. We need a way to distinguish them. So we give different names to the 2 copies. For example, instructor as T, instructor as S. Now SQL treats them as 2 different tables. T.salary refers to the salary from the first copy. S.salary refers to the salary from the second copy. This allows us to compare values between the 2 copies. This is called a self-join. A self-join means joining a table with itself. Continuing with part 2, self-join example, strings, like operator, order by, top/fetch, predicates, duplicates. OK, part 2 self-join example where we join a table with itself. We can compare rows within the same table. Suppose we have an instructor table. We create 2 versions of it, one called T, one called S. Now we can say, keep records, where T.salary is greater than S.salary. This means take an instructor from T and keep the record if their salary is greater than the salary of an instructor from S. This helps us find instructors with higher salaries compared to others. Now suppose we add another condition, S.department name is computer science. This means the comparison is only against instructors from the computer science department. So the result will show instructors from any department whose salary is higher than at least one computer science instructor. The as keyword is optional. You can simply write instructor T. This automatically gives the instructor table the temporary name T. However, renaming is very important when performing operations on the same table. Finding supervisors using self-join, consider a table containing a person and their supervisor. For example, Bob has supervisor Alice. Alice has supervisor David. Finding Bob's supervisor is easy. We can select a supervisor where the person is Bob. But finding the supervisor of Bob's supervisor is more difficult. We first find Bob's supervisor, which is Alice. Then we find Alice's supervisor, which is David. This can be extended to find all supervisors in the entire hierarchy. A Cartesian product and self-join concepts can help solve these kinds of problems. String value strings are very important in databases. Examples of string data include names, ID, department names, course names. Sometimes we need to match an exact string. For example, department name equals computer science. In this case, we directly use the string inside quotes. But sometimes we only know part of a string. For example, we want to find all instructors whose names contain the letters DAR. For this, SQL provides the like operator. The % symbol is used as a wildcard. A wildcard means it can represent any number of characters, including no characters. For example, %dar%. This means anything before dar, anything after dar. So it can match Darwin, Majumdar, Sardar, or any name where dar appears anywhere. If we write only dar%, it means the name must start with dar. It can match Darwin, but it will not match Majumdar because dar appears at the end. Similarly, %dar means the string must end with dar. Like allows different patterns for searching strings. String matching is case sensitive. This means uppercase and lowercase are treated differently. SQL also supports other string operations like combining strings, converting text to lowercase, converting text to uppercase. Order by clause after generating output. We often want the results arranged in a specific order. For example, alphabetical order, ranking order, increasing or decreasing values. SQL provides the order by clause for this. For example, select names from the instructor table. We may want only distinct names. Distinct means duplicate values are removed. Then we order the names. Since names are strings, SQL sorts them according to dictionary order. By default, ordering is ascending. Ascending means smaller to larger. For strings, it means A to Z. Descending means larger to smaller. For strings, it means Z to A. You can also specify multiple columns for sorting. For example, first sort by department, then by name. This makes output easier to read. Selecting only a certain number of rows, sometimes a query returns a very large number of rows. Displaying everything at once is inconvenient. For example, email inboxes show only some emails at a time. Bank statements show only some transactions. SQL allows selecting only part of the result. Different database systems use different syntax. Some databases use select top. For example, select top 10 rows. This means show the first 10 rows. MySQL uses limit. Oracle and standard SQL commonly use fetch first number of rows only. These commands allow selecting a specific portion of the output. It is similar to moving through pages of results. Where clause predicates the where clause is used to filter records. SQL provides convenient ways to write conditions. One example is between. Suppose we want instructors whose salary is between $90,000 and $100,000. Instead of writing two conditions, salary greater than or equal to 90,000 and salary less than or equal to 100,000, we can write salary between 90,000 and 100,000. This checks whether the value lies within the given range. Tuple comparison SQL also allows comparing multiple values together. For example, instructor ID equals teacher's ID, and department name equals biology. Instead of writing two separate conditions, we can compare the pair together. This is called tuple comparison. It is commonly used for equality comparisons. In operator, another useful operator is in. In checks whether a value belongs to a list. For example, instead of writing department equals computer science, or department equals biology, or department equals mechanical. We can write department in computer science, biology, mechanical. This makes queries shorter and easier to read. Duplicates in SQL in relational algebra. Duplicates are not allowed. This is because relational algebra is based on set theory. Sets cannot contain duplicate values. However, SQL allows duplicates. This is related to the concept of a multiset. A multiset is a collection where duplicate values are allowed. For example, if the same record appears multiple times, SQL keeps all copies unless we specifically remove duplicates. The distinct keyword is used when we want to remove duplicates. Without distinct, SQL behaves like a multiset system. For example, if a table contains A, B, a projection operation may still contain multiple of values. Similarly, when performing a Cartesian product, duplicate values can create multiple repeated combinations. SQL internally follows this multiset behavior. Module summary. This concludes the module. You may feel that SQL has many commands and syntax rules. With practice, these commands become easier. The upcoming tutorials will provide more examples and explanations. Keep the basic SQL syntax available for reference. Thank you.
Hello everyone. In this video, we are going to discuss the execution of SQL code from lecture 2.4, which is module 9. In the previous lecture, we discussed how to create a table, how to insert data into a table, and some DDL commands. Now let us see what we have in this particular module. In this module, we are going to discuss the Cartesian product first. Then we will discuss rename operation, string values, order by, select top or limit, where clause, predicates, and duplicates. Some of these concepts were already discussed in previous tutorials, but we will quickly revise them. Let us start with the basic operation. The first concept is the Cartesian product. Suppose we want to find the Cartesian product of the instructor table and the teacher's table. We have an instructor table and a teacher's table, and we perform a Cartesian product between these two tables. The SQL query for this is select asterisk from instructor, teachers. When we specify two tables separated by a comma, it means we are performing a Cartesian product or cross-join. A cross-join works the same way as a Cartesian product. The only difference is the syntax. Instead of writing select asterisk from instructor, teachers, we can write select asterisk from instructor cross-join teachers. Both queries produce the same output. So remember, a cross-join is basically a Cartesian product. Now, in the previous video, we discussed that if the instructor table has 10 rows and the teacher's table has 5 rows, then the Cartesian product will contain 10. 5 equals 50 rows. The resultant table contains combinations of every row from the first table with every row from the second table. For example, the first row of the instructor table will combine with all rows of the teacher's table. Then the second row of the instructor table will combine with all rows of the teacher's table, and so on. This is how we get 50 rows when one table has 10 rows and the other has 5 rows. We will also execute this Cartesian product or cross-join in SQL. Now let us look at an example. Find the names of instructors to have taught some courses and the corresponding course ID. We need to find the instructor name along with the course ID. If we perform a Cartesian product, we will get a large table. But from this table, we cannot directly get meaningful information. For example, one row may contain an instructor ID 10,101 name, Chassen department, computer science salary 65,000, but the teacher's table may contain a different ID, a different course ID, section ID, semester, and year. So if we want to know which courses were taught by instructor Chassen, we cannot get the correct answer from the Cartesian product alone. The reason is that a cross product simply combines every row with every other row. Therefore, we need to filter the output based on some condition. Here the condition is instructor.id equals teachers.id. We match the ID from the instructor table with the ID from the teachers table. After applying this condition, we remove unrelated combinations and get meaningful data. This type of join, where we compare a common attribute using equality, is called an equijoin. An equijoin works by matching a common attribute between two tables. For example, instructor.id equals teachers.id. This ensures that the output makes sense. Now let us execute this in pgadmin. First, we check the instructor table, select asterisk from instructor. After executing this query, we can see the instructor table. Suppose it contains 50 rows. Now let us check the teachers table, select asterisk from teachers. Suppose this table contains 100 rows. If we perform a Cartesian product between these two tables, the number of rows will be 50. 100 equals 5,000 rows. Let us execute the query and check. We get 5,000 rows. But again, this does not provide meaningful information because the ID do not match. So we apply an equijoin condition, where instructor.id equals teachers.id. Now, instead of 5,000 rows, we get 100 rows because we are matching the ID from both tables. Now the output becomes meaningful because each instructor is connected with the correct course information. For example, we can see the instructor's name, department, salary, course ID, section ID, semester, and year. This is how Cartesian product and cross-join work. If we replace the comma with cross-join, select asterisk from instructor cross-join teaches, the output is the same. The only difference is the syntax. Now one more important point. In a cross-join, number of rows equals R1, R2, where R1 is the number of rows in the first table, and R2 is the number of rows in the second table. The number of columns is number of columns equals C1 plus C2, where C1 is the number of columns in the first table, and C2 is the number of columns in the second table. For example, if the instructor table has 4 columns and the teacher's table has 5 columns, then the result will have 4 plus 5 equals 9 columns. Remember, this is for the Cartesian product without applying any where condition. Continuing with part 2 next. Go on part 2, now let us continue with the example. Find the name of all instructors in the art department who have taught some courses and the corresponding course ID. We need the instructor name and course ID. The instructor name comes from the instructor table, and the course ID comes from the teacher's table. So we need both tables. If we simply perform a Cartesian product from instructor teaches, we will get many rows, but the data will not be meaningful. To make the result meaningful, we need to filter using the common attribute, where instructor.id equals teachers.id. Additionally, we need another condition, instructor.department name equals art. This means we only want instructors from the art department. So the process is perform Cartesian product. Match the common attribute. Apply the required condition. This is how cross-join works. Now let us discuss rename operation. In previous queries, we repeatedly wrote full table names. For example, instructor.id teachers.id instructor.department name. Writing long table names again and again makes queries complicated. To solve this, we can rename tables using aliases. For example, instructor as I, teaches as T. Now instead of writing instructor.id we can write I.id instead of teachers.id we can write T.id. The keyword as is optional. We can also write instructor I teaches T instead of instructor as I teaches as T. Both work the same way. The purpose is only to make queries shorter and easier to read. Similarly, we can rename output column names. For example, if we want a different name for a column in the result, we can use an alias. Now let us look at another example. Find the names of all instructors who have a higher salary than some instructor in the computer science department. Here we need to compare the salary of one instructor with another instructor. For this, we use the same table twice. Example, from instructor as T, instructor as S here. Both tables contain the same data, but we treat them as two different tables. Now we compare T.salary, S.salary. This means the salary of instructor T should be greater than the salary of instructor S. Then we add S.department name equals computer science. This means we compare against instructors from the computer science department. The keyword as is optional and can be omitted. Now another example. Suppose we have a table called employee super. It contains person, name supervisor, name find the supervisor of Bob. The query is select supervisor from employee super where person equals Bob. The output gives the supervisor of Bob. Now find the supervisor of Bob's supervisor. Suppose Bob's supervisor is Alice. Alice's supervisor is David. The answer should be David. To solve this, we need to perform a Cartesian product on the same table and compare the supervisor relationships. This is an example of using a table with itself. The third question is, find all direct or indirect supervisors of Bob. This includes Alice, David, Mary, Susan, and so on. For this type of problem, SQL recursion and common table expressions can be used. A common table expression, or CTE, allows us to write recursive queries. You can also try solving it using Cartesian products, but recursion is the more suitable approach. Now let us discuss string operations in SQL. SQL provides pattern matching using percentage symbol %_ symbol. The percentage symbol matches any number of characters. The underscore symbol matches exactly one character. For example, matches one character. Percent matches any number of characters. We use these with a like operator. Example, find all instructors whose name contains the letter D. The query uses name like %D%. The first percentage allows any number of characters before D. The second percentage allows any number of characters after D. So D can appear anywhere in the name. Now suppose we want to match the exact string. 100%. The percentage symbol normally acts as a wildcard. To treat it as a normal character, we use an escape character. For example, 100%. The backslash tells SQL that the percentage symbol should be treated as a normal symbol. String pattern matching can also be case sensitive depending on the database system. Now some examples to find names starting with P. Name like P%. This means the first character must be P, and anything can come after it. To find names ending with E, name like %E. This means anything can come before E, but the last character must be E. To find names containing comp, name like %comp%. This finds any string where comp appears anywhere. Now using underscore, if we write 3 underscores mean exactly 3 characters. If we write %, it means at least 3 characters. The first 3 underscores require 3 characters, and the percentage allows any extra characters after that. Continuing with order by limit, where in, and not to next. Go on continuing from where left off, so this is how we can use the like operator in SQL along with the percentage symbol and underscore symbol. You can practice the like operator because we also have a graded assignment question based on this. Now let's discuss the next concept, the order by clause. Suppose we want to list the names of all instructors in alphabetical order. If I simply run select distinct name from instructor, I will get the instructor names, but they will not necessarily be sorted. If I want the output in sorted order, I can use the order by clause. For example, order by name. If we do not specify ascending or descending order, SQL uses ascending order by default. So, order by name ask and order by name give the same result. If we want descending order, we use order by name desk. We can also apply order by multiple attributes. For example, we can sort first by department name and then by instructor name. Now let's discuss the select TOP clause. The select TOP clause is used to specify the number of records we want to return. This is useful when dealing with large tables containing thousands of records. Returning all records can affect performance. For example, suppose the instructor table has thousands of rows. If I run select name from instructor, I get all names. But suppose I only want the first 10 names. Then I can use select top10 name from instructor. However, not every database system supports select top. For example, SQL Server supports select top. MySQL and PostgreSQL use the limit clause. Oracle uses methods such as fetch first, rows, or rowname. Let's try this in pgadmin. First, if we execute, select asterisk from instructor, we can see the instructor table. The names are not sorted. Now if we write, select asterisk from instructor order by name, the names appear in ascending alphabetical order. If we only want the first 5 rows, select asterisk from instructor order by name limit 5. Now the output contains only 5 rows. If we want the first 5 names in descending order, order by name desc limit 5, we get the 5 largest names in descending order. We can also use order by with salaries. Suppose we want the instructors with the top 3 salaries. We can write order by salary desc limit 3. Because higher salaries should appear first, we use descending order. This gives the 3 instructors with the highest salaries. Now suppose we want the instructor with the second highest salary. The highest salary is already the first row. We need to skip that row. For this, we use offset. Offset skips a given number of rows from the beginning. Example, limit 1 offset 1. This means skip 1 row. Return 1 row. So this gives the second highest salary. Similarly, limit 1 offset 2 gives the third highest salary. However, if 2 instructors have the same salary, this method may not always work correctly. In such cases, we use concepts like subsquares or aggregate functions, which we will discuss later. For now, understand order by sorts the output. Limit controls how many rows are returned. Offset skips rows. Now let's discuss the where clause. We already discussed where in the previous lecture. SQL provides the between operator for comparisons. Suppose we want instructors whose salary is between 90,000 and 100,000. Instead of writing where salary greater or equal 90,000 and salary less or equal 100,000, we can write where salary between 90,000 and 100,000. This gives the same result. Next is the AND comparison. Previously, when finding instructors from a department, we used multiple conditions. For example, where instructor.id equals teachers.id and department name equals biology, the AND operator allows us to combine multiple conditions. Both conditions must be true. Now let's discuss the IN operator. Suppose we want instructors from computer science or biology departments. Without IN, we write where department name equals computer science or department name equals biology. But if there are many departments, this becomes lengthy. Instead, we use where department name in computer science, biology. This checks whether the value exists in a given list. The output is the same. We also have the not IN operator. Suppose we want instructors from every department except computer science and biology. We write where department name not in computer science, biology. This removes those departments and returns all others. The values inside IN and not IN do not always have to be written manually. They can also come from another select query. For example, where department name in select department name from another table. This is related to the concept of subqueries, which we will discuss in upcoming lectures. So, in this lecture, we covered Cartesian product and cross-join, equi-join using common attributes, rename operation using aliases, string operations, like operator, percentage and underscore wildcards, order by clause, limit and offset, between operator, IN and not IN operators. These concepts help us write more powerful SQL queries. Thank you.
Welcome to Module 10 of Database Management Systems course in the IIT Madras online b.sc program. We are in the middle of learning SQL. In Module 8, we discussed the basic query structure, and in the last module we talked in more detail about additional operations, supporting features, and related concepts. Continuing from there, in this module we will discuss some more ways of performing operations in SQL. We will not be limited only to the basic query structure. This module will cover set operations, how null values affect queries, and results aggregate functions. These are the main topics we will discuss. Set operations, where we talk about set operations. We treat relations as sets. They are no longer considered multisets. Two relations can participate in a binary set operation such as union intersection difference, but there is a condition. Both relations must have the same structure. For example, we cannot perform a union between one relation having 3 attributes and another relation having 2 attributes. That would not make sense. Usually, set operations are performed between 2 different derived results of the same relation. Let us see an example. Suppose we have a courses table from the university schema. The table contains information like course ID, section, semester, year. We want to find all courses that ran in 2009 or 2010. First, let us find courses that ran in fall 2009. The query would be select course ID from section where semester equals fall and year equals 2009. This gives all courses that ran in fall 2009. Similarly, we can find courses that ran in spring 2010. Select course ID from section where semester equals spring and year equals 2010. Now, we want courses that ran in either fall 2009 or spring 2010. The word "or" can be expressed using the union operation. So, select course ID from section where semester equals fall and year equals 2009 union select course ID from section where semester equals spring and year equals 2010. Here we have 2 result tables with identical structures, and union combines the records. So union represents the logical OR operation. Now, suppose we want courses that ran in both fall 2009 and spring 2010. The query structure is similar, but instead of union we use intersect. Select course ID from section where semester equals fall and year equals 2009. Intersect select course ID from section where semester equals spring and year equals 2010. The result contains only the courses common to both sets. Now consider exclusion. Suppose we want courses that ran in fall 2009 but did not run in spring 2010. This is a set difference operation. The SQL keyword used is except. Select course ID from section where semester equals fall and year equals 2009 except select course ID from section where semester equals spring and year equals 2010. This means take the first result and remove everything that appears in the second result. These 3 operations, union, intersect, except, are very useful for writing different kinds of queries. Now let us look at another example. Suppose we have an instructor table containing salary information. We want to find the highest salary among all instructors. Normally, later we will see aggregate functions, which make this easy, but let us solve it using normal relational operations. How do we define the highest salary? A salary is not the highest when there exists another salary greater than it. So instead of finding the highest directly, we find all salaries that are not highest. A salary is not highest if salary some other salary to compare salaries. We need to compare the table with itself. This means we use a Cartesian product between 2 copies of the instructor table. We rename them instructor as T, instructor as S. Now we compare T.salary S.salary. This finds all salaries that have a larger salary somewhere else. The only salary that will not satisfy this condition is the maximum salary. After finding all non-highest salaries, we subtract them from the complete salary list. The remaining value is the highest salary. So the idea is get all salaries. Get all salaries that are not maximum. Remove the second set from the first using except. The remaining salary is the highest salary. The result is a table containing one value. This is different from aggregate functions, where we directly get the value itself. Set operations are powerful because they allow us to express queries using relational algebra concepts. Efficiency and optimization are separate topics, but here we are focusing on how expressive SQL can be. One important point: set operations treat relations as sets, not multisets. That means duplicates are removed. For example, union removes duplicates. But if we want to preserve duplicates, we use union all intersect all except all. Now duplicates are retained. For union all, if a tuple appears m times in relation or n times in relation s, then the result contains m plus n occurrences because nothing is removed. For intersect all, the common number of occurrences is kept. If R has a tuple 5 times and S has it 3 times, the result contains 3 occurrences. For except all, the difference is kept. If R has 5 copies and S has 3 copies, the result has 2 copies. But it cannot become negative. If R has 3 copies and S has 5 copies, the result is 0. Next, we discuss null values. A null value means an unknown value. Why is null important? Sometimes a value does not exist for every record. For example, every student may not have a passport. We should not store some random value, because later we would need to check whether that value is real or represents missing information. Null has a special meaning: I do not know the value. Another case is where we insert a record, but do not know all information yet. For example, when a student joins, the total credits may not be assigned yet. We cannot say it is 0. 0 means the student has taken 0 credits. Null means the credit information is not available yet. These are different meanings. When we add a new attribute to an existing table, old records may not have a value for that attribute. Those values are initialized as null until updated. So null has important consequences. When null participates in arithmetic operations, the result is null. For example, null plus 10 results in null. Now, how do we check for null? We cannot write salary equals null because null is not a normal value. Instead, we use salary is null. This checks whether the value is unknown. Similarly, salary is not null checks that the value exists. Null introduces 3-valued logic. Normally Boolean logic has true-false. With null, we add unknown, so SQL works with 3 truth values: true, false, unknown. For all true or unknown equals true, false or unknown equals unknown, unknown or unknown equals unknown for, and true, and unknown equals unknown false, and unknown equals false unknown, and unknown equals unknown for not, not unknown equals unknown for no, where condition evaluates to unknown. SQL treats it as false and does not include that row. This defines how null behaves in queries. Now let us discuss aggregate functions. We discuss 5 aggregate functions: avg, min, mix, sum. Count. These operate on a multi-set of values from a column. They return a single value. For example, finding average salary, select avg salary from instructor, where department name equals computer science. The where clause selects only computer science instructors, and avg calculates the average salary. Count can behave differently. Sometimes we want distinct values. For example, count distinct ID. Convert the multiset into a set before counting. For counting records, count asterisk is used. Here the star means any attribute, because we are only counting rows. Now consider finding the average salary in each department. If we simply calculate average salary, we get one average for the whole table. But we want separate averages for each department. This is done using group by creates groups of rows with the same value. For example, all computer science instructors together, all mathematics instructors together, all physics instructors together. Then the aggregate function is applied to each group. Example, select department name, AVG salary from instructor group by department name. The result contains department name average salary group by is useful whenever aggregation is required based on a category. One important rule: when using group by, every attribute in the select clause must either be part of the group by or be inside an aggregate function. You cannot select random attributes. Finally, we have the having clause. Where applies before grouping. Having applies after groups are formed. For example, first create groups using group by, then apply conditions using having. So, where filters rows, having filters groups. Null values also affect aggregate functions. Most aggregate functions ignore null values. For example, sum, AVG, min, max ignore null. Count asterisk counts all rows. If all values are null, count returns 0. Other aggregate functions return null. This completes our discussion of SQL features for this module. There are many more examples and concepts to cover. Practice these features using the University Database Schema. We will continue with more SQL concepts in the next module. Thank you.
Welcome to this module. In this particular video, we are going to discuss the SQL concepts from Lecture 2.5, which corresponds to Module 10. In the previous few lectures, we started learning SQL. We discussed how to create tables, different data types, constraints, and how to insert data into a table. In the previous video, we also discussed the select clause. In this module, we are going to discuss set operations in SQL. The concept is similar to what we have studied in mathematics, such as union, intersection, and except. However, there are a few important points about using these set operations in SQL. We will also discuss how to deal with null values, what null means, and how it behaves in SQL queries. Finally, we will discuss aggregate functions in SQL and how to use them along with the group by clause and having clause. Set operations first. Let us discuss set operations. Suppose we want to find the courses that ran in fall 2009 or spring 2010. We already know how to retrieve data from a table after applying conditions. For example, to find courses that ran in fall 2009, we write select course ID from section where semester equals fall and year equals 2009. This gives all course ID that ran in fall 2009. Similarly, to find courses that ran in spring 2010, select course ID from section where semester equals spring and year equals 2010. Now, both queries return course ID. If we want courses that satisfy either condition, we can use union, select course ID from section where semester equals fall and year equals 2009. Union, select course ID from section where semester equals spring and year equals 2010. The result contains all courses that ran in either fall 2009 or spring 2010. An important requirement for set operations is that the two queries must be union compatible. Union compatibility means the number of columns returned by both queries must be the same. The corresponding columns must have compatible data types. For example, this is valid. Select course ID from section union select course ID from courses. But this is invalid. Select name, course ID from section union select course ID from courses, because the first query returns two columns and the second returns only one column. Intersect. Now suppose we want courses that ran in both fall 2009 and spring 2010. We use intersect, select course ID from section where semester equals fall and year equals 2009. Intersect, select course ID from section where semester equals spring and year equals 2010. Intersect gives only the common records. Except suppose we want courses that ran in fall 2009 but did not run in spring 2010. We use except, select course ID from section where semester equals fall and year equals 2009. Except, select course ID from section where semester equals spring and year equals 2010. Except means take the result of the first query and remove the records present in the second query. If we represent the first query as A and the second query as B, union gives a union B, intersect gives A, intersect B, except gives A minus B, and B minus R are different. Finding the highest salary using except, consider the problem. Find the salaries of all instructors that are less than the largest salary. The first query, select distinct salary from instructor, where salary, some other salary, conceptually finds all salaries that are not the highest. Then we get all salaries, select distinct salary from instructor. If we subtract the smaller salaries from all salaries, select distinct salary from instructor, except select distinct salary from instructor, where salary, some other salary, the remaining value is the highest salary. This demonstrates one use case of except. Multiset operations normally union, intersect, and except remove duplicates because SQL set operations behave like mathematical sets. For example, A2, 2, 3, 4, 5, 5B2, 2, 3, 5, 8, a union B gives 2, 3, 4, 5, 8 duplicates are removed. Our intersect B gives 2, 3, 5, only common values remain. Our except B gives 4 because only 4 exists in A, but not in B. To keep duplicates, we use union all, intersect all, except all for union all. If a tuple occurs n times in one relation and n times in another relation, the result contains m plus n occurrences. For intersect all, the result contains minimum m n occurrences. For except all, the result contains maximum 0 m n occurrences. For example, if A has 5 copies of a value and B has 3 copies, then our except all B will leave 5, 3 equals 2 copies. Null values. Now let us discuss null values. Null does not mean 0. Null means either the value is unknown or the value does not exist. For example, a student may not have a passport. We can't store a fake value because later it becomes difficult to distinguish a real value from a placeholder. So databases use null. Null behaves differently from normal values. For example, 5 plus null results in null because the result is unknown. We cannot compare null using salary equals null. This does not work. Instead, we use salary is null example, select name from instructor where salary is null, to find values that are not null. Salary is not null. 3-valued logic. Normally Boolean logic has 2 values. True, false with null. SQL introduces a third value, unknown, so SQL uses 3-valued logic. For of true or unknown equals true, false, or unknown equals unknown, unknown, or unknown equals unknown for, and false, and unknown equals false, true, and unknown equals unknown, unknown, and unknown equals unknown for not, not unknown equals unknown when a where condition evaluates to unknown. SQL treats it like false and does not select that row. Aggregate functions. Now let us discuss aggregate functions. Aggregate functions operate on multiple values and return a single value. Common aggregate functions are avg min max sum count. Example, find maximum salary, select max salary from instructor. Find average salary, select avd salary from instructor. Find minimum salary, select min salary from instructor. Find total salary, select sum salary from instructor. Count counts values. Select count ID from instructor. Count asterisk counts rows. Example, select count asterisk from course. This counts all rows. But select count column name counts only non-null values in that column. Group by. Sometimes we do not want one global aggregate. For example, find average salary in each department. We use group by, select department name, avg salary from instructor. Group by department name. Group by creates groups of rows having the same department name and applies the aggregate function separately to each group. The output contains department name average salary. When using group by, any attribute in select that is not inside an aggregate function must appear in group by. Correct, select department name, AVG salary from instructor group by department name incorrect, select department name, ID. AVG salary from instructor group by department name because ID is neither grouped nor aggregated. Having clause where filters rows before grouping. Having filters groups after grouping. Example, find departments whose average salary is greater than 42,000. Select department name. AVG salary from instructor group by department name having AVG salary 42,000. We cannot write where AVG salary 42,000 because we works before aggregation. Null values with aggregate functions ignore null values. For example, SUM salary ignores rows where salary is null. The same applies to AVG min max sum except count asterisk. Count asterisk counts rows, including rows containing null values. If all values are null, count returns 0. Other aggregate functions return null. This completes the discussion of set operations, null values, aggregate functions, group by. Having clause practice these concepts using the university database examples. The integral part, which was 2 here, and the fractional part, which is 0.7148, together form the complete decimal number. So the binary number that we converted was equal to approximately 2.7148 in decimal. Now, this concludes the basic conversion between binary and decimal numbers. Next, we will discuss character encoding and how characters are represented inside computers. Characters and character encoding now. We know that computers internally understand only binary values, meaning only 0 and 1. But humans do not work with only numbers. We work with characters such as letters, digits, symbols, and special characters. So the question is, how does a computer store characters? The answer is character encoding. Character encoding is a method of assigning a unique number to each character so that the computer can store and process it. For example, the letter A is not directly stored as the letter A inside memory. Instead, it is converted into a numeric value, and that numeric value is stored in binary form. So every character has a corresponding numerical representation. One of the earliest and most commonly used character encoding systems is ASCII. ASCII stands for American Standard Code for Information Interchange. It assigns numbers to characters. For example, capital letter A has the decimal value 65. Capital letter B has the decimal value 66. Capital letter C has the decimal value 67. Similarly, lowercase letters, digits, and special symbols also have their own values. Since computers store everything in binary, these decimal values are internally converted into binary. For example, the character A has an ASCII value of 65. The decimal number 65 in binary is 1,000,001, so internally, the computer stores the binary representation of the character. ASCII originally used 7 bits. Since 7 bits can represent 2 equals 128 different values, ASCII could represent 128 different characters. These included uppercase letters, lowercase letters, digits, punctuation symbols, control characters. However, as computing expanded globally, 128 characters were not enough because different languages have thousands of characters. This led to the development of more advanced encoding systems. One such system is Unicode. Unicode is a universal character encoding standard designed to represent characters from almost all writing systems around the world. It includes characters from English, Hindi, Chinese, Arabic, Japanese, many other languages. Unicode assigns a unique code point to each character. For example, the character A still has the code point U plus 0041. The computer then stores this code point using an encoding format such as UTF-8, UTF-16, or UTF-32. UTF-8 is one of the most widely used encoding formats today. UTF stands for Unicode Transformation Format. UTF-8 represents characters using a variable number of bytes. A character may use 1 byte, 2 bytes, 3 bytes, 4 bytes depending on the character. For example, common English characters use only 1 byte in UTF-8,
while many other symbols and languages require more bytes. This makes UTF-8 efficient, because it saves space for commonly used characters. Binary operations. Now we will discuss some basic operations on binary numbers. The basic operations are similar to decimal arithmetic: addition, subtraction, multiplication, division. Let us first discuss binary addition. The basic rules of binary addition are 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, 1 plus 1 equals 10 here. 1 plus 1 gives 10, because binary only has 2 digits. The result has a sum bit of 0 and a carry of 1. For example, 1011 plus 0011 minus 1110, we add from right to left. The rightmost position, 1 plus 1 equals 10, so we write 0 and carry 1. Then continue the same process for the remaining bits. Binary subtraction follows similar rules: 0, 0 equals 0, 1, 0 equals 1, 1, 1 equals 0, 0, 1 requires borrowing. Borrowing works similarly to decimal subtraction, but since binary has base 2, borrowing gives a value of 2. For example, 1010 00110111, the same idea of borrowing is applied. Binary multiplication is also similar to decimal multiplication. The rules are 0. 0 equals 0, 0. 1 equals 0, 1. 0 equals 0, 1. 1 equals 1. Since multiplication with 1 keeps the value unchanged, binary multiplication becomes relatively simple. Example, 101. 11 minus 101, 101 minus 1111. Binary division follows the same principles as decimal division. The difference is that the calculations are performed using only 0 and 1. So these are the basic concepts of binary numbers: decimal conversion, character encoding, and binary operations. These concepts form the foundation of how computers represent and process information internally.
Number representation in computers. Hello everyone. Today we're going to discuss a new topic: number representation in computers. In computer science, we need a way to represent numbers, characters, and different types of data inside a computer system. A computer does not understand normal human-readable numbers and characters directly. Everything inside a computer is represented using binary values, which means combinations of 0 and 1. So, we need proper representation methods to store and process information. Number systems in computers. A number system is a method of representing numbers using a set of symbols and rules. In daily life, we generally use the decimal number system. The decimal system has base 10 digits, 0 to 9. Computers, however, use the binary number system. Binary has base 2 digits, 0 and 1. The reason computers use binary is because electronic circuits have 2 stable states. On state OFF state, these states can be represented easily using binary. 1 represents on, 0 represents OFF. Therefore, binary is suitable for digital electronic systems. Representing characters in computers. Now the question is, how does a computer store characters such as letters? For example, A, B, C, numbers, and symbols. A computer cannot directly store the letter A. It converts characters into numbers. This process is called character encoding. A character encoding system assigns a unique numerical value to every character. For example, in ASCII American Standard Code for Information Interchange, character A has the value 65, character B has the value 66. These numbers are then stored internally as binary values. ASCII representation. ASCII is one of the earliest character encoding standards. It uses 7 bits. Since 7 bits can represent 2 equals 128 values, ASCII can represent 128 different characters. These include capital letters, small letters, numbers, special symbols, control characters. For example, the ASCII value of R is 65. The binary representation of 65 is 1,000,001, so the computer stores the binary form instead of the actual character. Boolean operations and logic. Computers also perform logical operations. A Boolean system works with 2 values. true, false. These are represented as 1. True, 0. False. The basic boolean operations are and operation. The output is 1 only when both inputs are 1. Example, 1 and 1 equals 1 1 and 0 equals 0 0 and 1 equals 0 0 and 0 equals 0. Or operation, the output is 1 if at least one input is 1. Example, 1 or 1 equals 1 1 or 0 equals 1 0 or 1 equals 1 0 or 0 equals 0. Not operation not reverses the value. Not 1 equals 0, not 0 equals 1. These logical operations form the foundation of computer processing. Binary arithmetic. Computers also perform arithmetic operations using binary numbers. The main operations are addition, subtraction, multiplication, division, binary addition rules. 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, 1 plus 1 equals 10. When adding 1 plus 1 in binary, the result becomes 10 because binary only has 2 digits. The 0 is written as the result and 1 is carried forward. Example, 101 plus 0, 11 minus 1000. Binary subtraction follows similar rules. The basic cases 0 0 equals 0, 1 0 equals 1, 1 1 equals 0. When we need to subtract 1 from 0, borrowing is required. Binary multiplication is also similar to decimal multiplication. Rules 0. 0 equals 0 0. 1 equals 0 1. 0 equals 0 1. 1 equals 1. Because binary has only 2 digits, operations become simpler for electronic circuits. Summary. In this lecture, we learned computers represent data using binary numbers. Binary uses only 0 and 1 because electronic circuits have 2 states. Characters are represented using character encoding systems like ASCII. Boolean operations are the basis of computer logic. Binary arithmetic allows computers to perform calculations internally. These concepts are fundamental for understanding how computers store and process information.
Hello everyone. In this tutorial, we will learn how to execute different SQL commands in the PostgreSQL platform. We will be using the PostgreSQL shell, which is called psql, for the entire task. We will perform this on Windows using the command prompt. The same thing can be done using a terminal in Ubuntu. Let us start. First, we need to open the command prompt because we are using the Windows platform. If you are using Ubuntu, you need to open a terminal. Next, we need to start the psql prompt. To do that, we write psql username here. U is used to specify the user ID. The default user ID is Postgres. After entering this, it asks for the password. I'm using the default password, which is also Postgres. If you have changed the password, you need to use your modified password. Now, if you want to see the databases that already exist inside PostgreSQL, you can use \l. This command lists all the databases currently available. Suppose we want to create a new database. We write create database company. Do not forget the semicolon at the end. The message confirms that the database has been created. If we again run \l, we can see the new database named company. Now, how do we enter this new database? We use \c company. This connects us to the company database. You can see that we have moved from the default PostgreSQL database into the company database. Now, when we are inside the company database, we can check what tables exist. We use \dt. Since we have not created any tables yet, it says that no relations exist. So, we need to create tables. Creating the department table first. Let us create a department table. The command is create table department dno int primary key. Dname varchar 40. Here, dno means department number. int means integer type. Primary, ky means this value must be unique and cannot be null. Dname stores the department name. Varchar 40 means a variable length character string with a maximum length of 40 characters. The table is now created. To see the structure of the table, \d department, this displays the table structure. We can see that the table has 2 columns, department number dno, department name dname. The primary key is dno. Creating the employee table now. Let us create an employee table. Create table employee int primary key in nam varchar 40 not null. DNO int references department DNO. Here, id is the employee ID and nam is the employee name. Not null means the name cannot be empty. DNO is the department number. The DNO column is a foreign key. A foreign key creates a relationship between tables. Here, the employee's department number must exist in the department table. Checking the structure, \d employee shows the columns and the foreign key relationship. Inserting data into tables now. Let us insert values into the department table. Insert into department values 101 CSE, 102 HR, 103 IT, 104 mechanical. Each row gets inserted. If we try to insert another department with the same department number, insert into department values 103 mechanical, it gives a duplicate key error. This happens because DNO is a primary key, and primary keys cannot repeat. To see the table contents, select asterisk from department. This displays all records. Inserting data into employee table now. Insert employees. Insert into employee values 10 Raj, 101 20 John, 102 30 Vaskar, 103 40 Arup, 103. If we insert another employee with the same employee ID, it gives a duplicate key error because id is the primary key. Similarly, if we try insert into employee values 50 Ram, 110, it gives a foreign key violation because department number 110 does not exist in the department table. An employee cannot belong to a department that has not been created. To view employees, select asterisk from employee, Cartesian product now. Let us perform a Cartesian product. A Cartesian product combines every row of one table with every row of another table. Command, select asterisk from employee, department. Since there are 4 employees and 4 departments, 4 equals 16 rows are produced. Every employee is combined with every department. Joining tables usually. We do not want every combination. We want matching departments. We add a condition. Select asterisk from employee, department, where employee.dno equals department.dno. This keeps only the rows where the department numbers match. The same operation can be done using a join. Select asterisk from employee inner, join department on employee.dno equals department.dno. This is called an inner join. It returns only matching rows from both tables. We can also give aliases to tables. Example, select asterisk from employee inner join department D on e.dno equals d.dno. Here, E represents the employee table, D represents the department table. Deleting data. Suppose we want to delete an employee whose ID is 40. We write delete from employee where id equals 40. One row is deleted. Checking again, select asterisk from employee. Shows that employee 40 is removed. If we want to delete all rows, delete from employee. The table remains, but all data is removed. Dropping a table. Deleting rows is different from deleting the table itself. To delete the entire table structure, drop table employee. Now the employee table no longer exists. Dropping a database. Finally, suppose we want to delete the entire company database. We cannot drop a database while we're currently inside it. So first we move back to PostgreSQL, \c Postgres. Now we can delete, drop database company. The database is removed. To exit PSQL, \q. In this tutorial, we learned how to execute basic SQL commands in PostgreSQL. Creating databases, creating tables, primary keys, foreign keys, inserting data, selecting records, joining tables, deleting rows, dropping tables, dropping databases. Practice these commands as much as possible to become comfortable with the PostgreSQL platform. Thank you for watching.